What if everything you've ever known, your home, your friends, your triumphs and failures, was just one version of reality? And somewhere, out there, another you exists. Maybe richer, maybe poorer, maybe a version of you that never watched this video at all. This isn't science fiction. It's one of the most radical ideas in modern physics, the multiverse. The shock of the question. For centuries, the universe meant everything. All of space, all of time, all that exists. That was the boundary of imagination. But physics has a habit of destroying boundaries. Once, Earth was thought to be the center of everything. Then the sun, then the galaxy, then countless galaxies beyond. At each step, what we thought was the whole turned out to be a tiny part of something bigger. So the next question almost feels inevitable. What if even our universe is just one among many? The deep roots of the multiverse. This isn't a new thought. The Greek philosopher Anaximander imagined countless worlds being born and dying in an eternal cycle. In Hindu cosmology, the universe itself is reborn endlessly through cycles of creation and destruction. Even in Norse mythology, there were multiple realms, 9 worlds held together by the great tree Yggdrasil. The human mind has always whispered of other worlds, but only now, through science, are we daring to test if it could be real. A quote that opens the door. As cosmologist Andre Linda once said, "The universe is not only queerer than we suppose, it may be queerer than we can suppose." The multiverse is that queerness. A possibility so vast it challenges not just science, but philosophy, religion, and identity. Because if there are infinite universes, what does that mean about you? The student's question. Imagine yourself in a classroom, looking up at a blackboard where the professor has written 2 words. Why us? Why this universe, with these laws of physics perfectly balanced to allow stars, planets, and life? Why not a universe where gravity is too strong and everything collapses, or too weak and nothing forms at all? This is the fine-tuning problem, and the multiverse is one possible answer. Not because our universe is special, but because there are infinite universes and we just happen to live in one where life is possible. This is where the journey begins. The question that breaks reality. If our universe is not unique, what else is out there? If the multiverse has a doorway, it begins here, in the smallest scales of reality, where the rules of the universe start to break. Welcome to quantum mechanics. 1. The double-slit mystery. In 1801, Thomas Young performed a simple experiment with light. He shone it through 2 slits and watched as it created an interference pattern, waves overlapping, rippling like water. But when the experiment was repeated with single electrons, something impossible happened. If you didn't look, the electron acted like a wave, passing through both slits at once. If you observed it, it collapsed into a particle, going through only one. It was as if reality itself cared whether it was being watched. Durch Schrödinger's cat. In 1935, Erwin Schrödinger illustrated this strangeness with a cat in a box. Inside, a vial of poison triggered by a quantum event. Until the box is opened, the cat is both alive and dead. 2 contradictory states coexisting. This is quantum superposition, but it raises a disturbing question. When does possibility become reality? 3. Hugh Everett's radical answer. In 1957, a young physicist named Hugh Everett gave an answer so radical, it was almost ignored. What if the cat isn't both alive and dead in one universe? What if reality splits? In one universe, the cat lives. In another, it dies. In one, you're watching this video. In another, you never click play. This is the many worlds interpretation. Every quantum event doesn't collapse into one outcome. It branches into all of them, across infinite universes. 4. A quote that changes everything. As Everett's colleague Bryce DeWitt later wrote, every quantum transition taking place on every star, in every galaxy, splits our local world into myriads of copies. It means reality isn't a single thread. It's an endless, branching tree. Every choice, every chance, every possibility lives somewhere. 5. The human angle. Think about it. There could be a universe where you chose a different career, where you met a different partner, where your ancestors made different choices that changed your life completely. The multiverse isn't just a theory about physics. It's a theory about you. And if every possibility exists, what does that mean for free will? Are we choosing our lives, or just living in one branch of infinite possibilities? Every grand theory of the cosmos begins with a problem, and the early universe had many. Why is the universe so flat, like a vast tabletop? Why do opposite ends of the sky, so far apart that light hasn't had time to travel between them, share the same temperature down to a few millionths of a degree? Why do we see so few relics, like magnetic monopoles, that some early theories predicted should litter the universe? For decades, cosmologists stared at these puzzles. Then came inflation. Section A, the idea of inflation. In the earliest fraction of a second, about 10 power 36 seconds after the Big Bang, space itself may have entered a runaway expansion. Not just fast, but exponentially fast. Imagine a balloon not just inflating, but doubling in size again and again, each doubling faster than the last. In less than a heartbeat, the universe grew from subatomic to cosmic scales that burst smoothed out wrinkles, stretched away curvature, and diluted exotic relics. Problem solved. Think of a crumpled piece of paper. Inflation is like tugging it until it becomes almost perfectly flat. The folds don't disappear, they just get stretched beyond what you can see. Section B, eternal inflation. Here's the twist. Inflation might not end everywhere at once. Quantum fluctuations, tiny jitterings of fields, mean that while inflation stops in one region, it can keep roaring in another. The result? A patchwork. Our visible universe is one such patch, a bubble where inflation ended. But elsewhere, bubbles keep forming, each with its own laws, constants, and physical fabric. Imagine dough rising with raisins inside. Each raisin is a bubble universe where inflation has ceased. But the dough, space itself, keeps stretching forever. Most of the bread is still inflating, birthing infinite raisins. This is the multiverse, born not of philosophy, but of physics. Section C, signs in the sky. If eternal inflation is real, what would we see? Cosmic microwave background, CMB's subtle patterns, cold or hot circles that might hint at bubble collisions. Some teams claim to spot them, but results remain contested. Primordial gravitational waves, ripples from the violent stretching, could leave a unique polarization pattern in the microwave sky. Experiments like BICEP and the upcoming Lightbird are on the hunt. Statistical fingerprints, the precise tilt of density fluctuations, the balance of smoothness versus clumping. These are predictions inflation makes, and observations so far largely line up. But direct proof of other bubbles? That remains elusive. We see shadows, not the thing itself. Section D, why it matters. Eternal inflation changes the story of creation. No longer is there one Big Bang. Instead, there are countless bangs, each hatching its own cosmos. And our universe? Just one bubble in a frothing sea. Some find this breathtaking, others unsettling, because it challenges the very idea of uniqueness. But science is not in the business of comfort. It is in the business of truth. So inflation doesn't just solve puzzles. It opens a Pandora's box. If bubbles keep forming, reality is bigger and stranger than our instruments may ever capture. But inflation is not the only path to a multiverse. Quantum mechanics, too, has something radical to say. And in Chapter 4, we meet Hugh Everett in the many worlds. Quantum mechanics, the strangest, most successful theory in science. It predicts the colors of atoms, the semiconductors in your phone, the lasers in your grocery scanner. And yet, its interpretation splits physicists into camps that sometimes feel more like philosophers. At the heart lies a riddle. When we measure a quantum system, why do we see one outcome instead of the blurry superposition that the mathematics describes? Section A, the old story, collapse. In the 20th century, the orthodox answer was what's called the Copenhagen interpretation. It said, before measurement, particles exist in a wave function of probabilities. When you measure, that wave function collapses. The fuzz resolves into one concrete reality. It was pragmatic. It worked in a lab, but it left a sour taste. Collapse was special, unphysical, tacked on. Why should nature follow one law until a human or machine looks and then suddenly play by another? Section B, Hugh Everett's bold proposal. Enter Hugh Everett, 1957, a 27-year-old graduate student at Princeton, fed up with magical collapses. His idea? Simple, but radical. What if the wave function never collapses? What if it always evolves smoothly by Schrödinger's equation? No exceptions. In that case, when a measurement happens, the universe itself branches. One branch for each possible outcome. In one, the particle is here. In another, it's there. You see one because you're now entangled with that outcome. Another you exists in the other branch, entangled with the other result. Section C, the river analogy. Imagine a great river flowing downhill. At each fork, it splits into channels. Each channel continues, complete, self-contained. You, the observer, are like a boat carried by the current. At a fork, you follow one channel, but the other channels are just as real, carrying other versions of you downstream. There's no collapse, just branching. The mathematics doesn't break. Section D, why this isn't science fiction. Many worlds is often misunderstood. It doesn't say universes pop into being in some extra space. The branches exist in the abstract structure of quantum mechanics, Hilbert space. They don't interact. They don't communicate. And it's not mere fantasy. The equations of quantum theory already describe this branching. Everett's move was simply to stop cutting the math short with an extra collapse rule. In fact, the theory is simpler this way. Richard Feynman once quipped, "I think I can safely say that nobody understands quantum mechanics. Many worlds is an attempt not at fantasy, but at consistency." Section E, experimental echoes. Can we test it? In principle, yes. Because if collapse were real, at some scale we'd see deviations. Experiments are scaling up interference to ever larger molecules. Thousands of atoms, still no collapse. Quantum computers, in a sense, are bets that Everett was right. They exploit superpositions that under collapse shouldn't persist. Many worlds doesn't predict anything different in the lab. It predicts no collapse, ever. If collapse is someday detected, many worlds falls. Until then, it remains one of the cleanest explanations. Section F, the psychological shock. Here's where it cuts deep. If branching is real, then at every quantum event, countless versions of reality are created. Countless versions of you. Some physicists wave it away. So what? You never meet them. Others wrestle with the implication that free will, uniqueness, even moral weight might feel different in a branching cosmos. Does it diminish this you? Or does it remind us that your choices in this branch matter? Because this is the only channel you will ever feel? So the multiverse may not just be out there in cosmic space, bubbling away. It may be hidden in the mathematics of every atom, every photon, every decision. The universe is written in laws, gravity, electromagnetism, the strong and weak forces, the constants of nature. But what if those laws weren't unique? What if the numbers we memorize as fundamental were not carved in stone, but simply local settings like dials tuned in one bubble among countless others? That's the shocking idea that emerges from string theory and the so-called landscape problem. Section A, strings and extra dimensions. String theory began as a way to unify everything: matter, energy, space, and time. At its heart, the idea that the fundamental building blocks of reality are not point particles, but tiny vibrating strings. Their different vibrations give rise to quarks, electrons, photons. But strings don't sing alone. They require extra dimensions, 6 or 7 of them, curled up so small we can't see them. The way those dimensions fold, twist, and compactify changes the physics that emerges. It's like a cosmic instrument with hidden strings. Tune it one way, you get one symphony of laws. Tune it differently, you get another universe altogether. Section B, the landscape of possibilities. Here's where it gets staggering. Calculations suggest that string theory allows not just a few ways to compactify these dimensions, but perhaps 10 power 500 possibilities. Each one corresponds to a different vacuum state, a different universe with its own constants, forces, and particles. This vast menu is called the string landscape. Picture a mountain range with countless valleys. Each valley is a possible universe. Our cosmos is one valley where the laws of physics settled after the Big Bang. But the landscape has valleys beyond imagination, most inhospitable, some fertile. Section C, the anthropic principle. Why does our universe allow life at all? The cosmological constant, the energy of empty space, could have been trillions of times larger. If it were, galaxies would never form, stars would never ignite. So why this value? Why these dials? Enter the anthropic principle. It says, we observe these laws because only universes with these laws can support observers. In other words, we're not special. We're just survivors in a cosmic lottery. This isn't an explanation of why the landscape exists. It's a selection effect, like asking why you find yourself on a life-friendly planet instead of a frozen rock. Because on the rock, you wouldn't be here to ask. Section D, the controversy. To some physicists, this feels like surrender. Science should explain numbers, not shrug and say, we live here because we can. Steven Weinberg, however, used the anthropic principle to predict the cosmological constant's order of magnitude before it was measured. It was eerie, and it came true. So is the anthropic principle a cheat code or a clue? I want to know if God had any choice in creating the universe. The landscape suggests, maybe yes, too many choices. Section E, a universe among many. If the landscape is real, our universe is not the unique product of deep symmetry, but one island in an archipelago of universes. We are not privileged, just fortunate. Some physicists see this as liberation. Physics is richer than we dreamed. Others see it as a dead end. How do you test universes you can never reach? Yet perhaps the test is indirect. Whether the landscape makes sense of fine-tunings that would otherwise be absurd. So we arrive at a crossroads. Either the constants are unique and demand a deeper law yet undiscovered, or the landscape is real, and we're one valley among many. But whichever way, the question lingers. Can we find evidence? Can we catch even a shadow of these other worlds? That's where we go next. What would count as proof? Tonight we've seen how inflation, quantum theory, and string theory all point to a multiverse. But can we ever find evidence? Can it be tested or even falsified? That's what we explore in part 2. Watch it now in the Cosmic Mysteries playlist and keep the journey going.